Bismillahirrahmanirrahim. All right, class, and welcome to the second lecture of week 5. So, we were discussing the Coulomb's law, and particularly we were saying that Coulomb's law is linear, and that consequence of linearity is that we can apply superposition, and we talked about a little bit about superposition, which you already know in terms of circuit analysis. Alright, so before removing this from the board, I can just write an equivalent of this or that final expression, and that would be just resolving what the unit vector is. Let's say I've got this F12, so this is nothing but Q1 Q2 upon 4 pi epsilon naught magnitude of R12 squared, and this unit vector AR12, which is nothing but R12 and divided by its magnitude. Divided by its magnitude means that I can simply make it, instead of square, I can make it cube. So this is another way of writing it. So similarly, I can write this force as Q1 Q2 upon 4 pi epsilon naught magnitude of R21 cubed multiplied by the vector R21. So this is another way of writing it. Sorry, this is cube. Okay, this is another way of writing it. All right. So, what does it mean by Coulomb's law is linear? Let's see that. Let's say I have got this point charge Q here, Q1 again, and this point charge is Q2. Let's say again both are positive or negative. I mean, both are like charges, meaning that in any case both will repel each other. So the line joining these two is given by R, whether 1 2 or 2 1, that will be depending on the question or the point at which we want to evaluate the force. So let's say I want to, that's clear that both the point charges will repel each other, and the force of repulsion will be acting along the line joining the 2 point charges. That's clear. So if I am interested in the force on 2 due to 1, okay, or let's say the force on 2, okay, so in that case what I have to do is to write force on 2 is equals to nothing but Q1 Q2 upon 4 pi epsilon naught. I want a vector in this direction, so I want a head on point 2, so head on point number 2, tail on point number 1. So this vector should I should find. So subtract the coordinates of head point from the respective coordinates of the tail points and multiply by unit vector. You know how to evaluate R21. So R21 divided by magnitude of R21 cubed. So we'll get what? We'll get force on 2. Okay, so let's say, for the sake of argument only, let's say the value is of Q1 is 1 millicoulombs, okay, and somehow magically the distance is such that, not magically, scientifically, the distance is such that the force on 2 comes out to be, let's say, 1 Newton. So what is the meaning of this? So applying superposition, the meaning is that if for the same arrangement, if I just multiply, if I just increase the value of charge, instead of 1 millicoulomb, I make it 10 millicoulomb. That means that I have multiplied the charge by 10. So if the source is multiplied by 10, then its effect, which is the force on charge Q2, should be multiplied by 10. So if I had known that the force on 2 is 1 Newton, if the charge Q1 is 1 millicoulomb, then I don't need to recalculate everything in order to find the force on the same point, that is Q2, charge Q2 with respect to the charge Q1, which is now 10 times the previous case. So I would simply say that since Coulomb's law is linear. Since the source has been multiplied by 10, the effect will also be multiplied by 10. I don't need to reevaluate anything. I don't need to recalculate anything. Okay, so this is first consequence of superposition. Input multiplied by 10, output multiplied by 10 blindly. Okay, the second consequence is, now I'm just removing this case because we have done it. All right, so the second consequence is that if there is more than one source, instead of only Q1, we have got Q2 as well, Q3 as well, and now we want the force on point number on the point at which Q2 is located. So I want to find the force on again Q2. This time the second aspect of superposition will come into play, that the effect, the total effect at this point due to Q2 and Q3 will be the sum of individual effects of Q1 and Q2. That's simple. So now I cannot write it like this individually, because now this is not the total force on Q2. Why? Because I've introduced another force Q3. So I should better write it like this: force on 2 due to 1. Yes, force on 2 due to 1 is now this. Okay, force on 2 due to 1 is now this, and let's say again this charge is positive. Okay, if all are positive, let's say all are positive, then the force on 2 due to 3 should be evaluated. Now this one is the force at this charge Q2 only due to Q1, so the force on this charge Q2 only due to Q3 should be equals to product of the two charges Q2 Q3 divided by 4 pi epsilon naught. And since this force will be, you know, acting along the line and repulsive, so this is force F21. Let me write it here, F21, and this force is F23, force on 2 due to 3 Q3. Okay, and now for this I would need a vector in this direction, meaning I know this point, I know this point, so I need a vector which has got a head over here and tail over here. So what I would need is, I would need R2, 3. Okay, head and tail. So magnitude of 2, 3 cubed and 2, 3. That's it. Now the second aspect of superposition says that the total force at this point 2, which is F2, is equals to the individual forces, force on 2 due to 1 plus force on 2 due to 3. Okay, so F2 is nothing but Q1, Q2, or if I take, you know, 1 upon 4 pi epsilon naught common, so it will be Q1, Q2 R21 divided by magnitude of R21 cubed plus Q2, Q3 R23 divided by magnitude of R23 cubed. This would be the final answer. Okay, and this can be extended up to n number of source charges. Okay, n number of source charges. So this is the second consequence of applying superposition theorem. All right, so so far we have discussed Coulomb's law. The title of the chapter is Coulomb's law and electric field intensity. So far we have discussed Coulomb's law and elaborated much on it. So let's talk about the second topic of this chapter, which is electric field intensity. So what is electric field intensity? All right, so In order to study a point charge, let's say this point charge Q1, now I'm not giving it any subscript, and I want to study the field of this static charge, or the electrostatic field I want to study. So for that, what I have to do, I have to, obviously this electrostatic field would be bounded in some closed space, volume, three-dimensional volume. And if I want to study the effect of this charge, so we know that this charge would only affect other charges which also have which also have certain fields surrounding them, just as the case of gravitational field, that the gravitational field affect other masses which have a gravitational field surrounding those masses. So the effect of this charge is felt by another charge in the form of force. So this charge has got a force field surrounding it. So if I want to quantify that field, if I want to discuss about that field, if I want to if I want to focus on the field which is given by this charge, then that field should not have any influence of the second charge which is coming within the field of this charge. Okay, so just as the case of gravitational field, of just as the case of Earth and Moon, the scenario which I sketched earlier in the previous lecture, if I want to talk about this charge or field of this charge, and this field, the field of this charge should not depend on any other charge which is present within the field of this charge. Let me, instead of calling repeatedly this charge, let me call it source charge. Okay, if I want to find or specify or discuss or define the field of the source charge, what I need to have certain formula which should be independent of any other charges, which should have only QS in that formula, or in that discussion, or in that specification, or in that definition. The only thing which should be there is the QS, that is the source charge. Can we use the formula for Coulomb's law to define the force on this second charge, which we normally call as the field charge? So the force on field charge due to source charge is equals to source charge, test charge, and 4 pi epsilon naught. And we know that let's say this is a positive charge and this is also a positive charge. So in that case, the distance between the two, we need to have a vector which should have a head here, because it will push it away. So head minus tail, RTS is what we need. So RTS magnitude cubed and multiply by vector RTS. This is what we would need. And if, let's say, the test charge is negative, if let's say the test charge is negative, I'm writing it in red, in that case the force on the test charge due to source charge is equals to QS QT divided by 4 pi epsilon naught. This time, since it will attract, because this is positive, this one is negative, positive, negative, it will attract. So force will be opposite to the previous case. So now we need RST instead of RTS, and the magnitude of RST cubed. This is what we need. So which formula should I use, either this or this, in order to define the field of the source charge? This formula is for positive test charge. This is for negative test charge. This should not be the case. It's just like, Tendulkar and Shoaib Akhtar's example I talked about. If I'm trying to define the characteristics of how Tendulkar plays, that should not be depending upon the bowler in front of it. Okay, if he is a good batsman, he is a good batsman. That's it. Okay, so Similarly, if I'm talking about the characteristics of this QS, I don't need that. Those characteristics should not depend on the charge, the test charge. Okay, so it means that this test charge has to be removed from this formula somehow. It means that we should fix the judge, you know, try to relate it to with the gravitational example. We should have a judge here which will be used to evaluate the field of every charge which is present or which might be present in this universe. All right, and that charge that judge charge has been specified by the scientific community is to be the unit positive charge of 1 Coulomb. So QT should always be 1 Coulomb, which is a huge charge. So to make QT 1 Coulomb, what I can do, I can write, what I can do is I can divide the formula for force field of this source charge. Okay, I should divide that by QT in order to get QS upon 4 pi epsilon naught R TS cubed into R TS. This is what. Now I've got something on the right hand side which is independent of the test charge, or in other words, I have made this test charge to be equals to +1, and this definition of force is called electric field intensity. Okay, this is electric field intensity, force experienced by 1 Coulomb plus 1 Coulomb charge, which is the judge charge, which is going to be the judge charge for every possible charge within this universe, no matter if this QS is 1 millicoulombs or 1 megacoulombs, which is extremely high, or 1 nanocoulombs, or if it is minus 3.4 nanocoulombs, or if it is minus 7 millicoulombs, whatever the value of this QS may be, the test charge, the judge charge will always be positive 1 Coulomb. Only then the formula or the comparison or the force field felt by this 1 Coulomb judge charge would give us results which would be fair to compare with each other, just as the case was just as the case which we discussed in the scenario of Earth and Moon gravitational fields. Okay, so having said that, now we have got a formula for electric field intensity, which is nothing but force force of the source charge divided by test charge. Okay, which on the right hand side is nothing but QS into R divided by 4 pi epsilon naught R cubed. Okay, so notice that I have I just got rid of the subscripts associated with the source. I can write its source, but I'm not going to write it here, just to get rid of the unnecessary subscripts. So let's say we have got origin here. Okay, and let's say this is charge QS. Okay, and it has got a field surrounding it. I'm not going to draw it, and I want to find the value of field at this point, electric field intensity at this point. So you should remember that finding electric field intensity at this point means that I am placing a +1 Coulomb charge over here, and I'm trying to find the force which that +1 Coulomb charge would experience due to this source charge. Okay, so this point, any point within the field of the source charge where I would put that +1 Coulomb judge charge, the judge charge which is +1 Coulomb, that point is known as field point. Okay, we'll call it field point. So wherever I want to evaluate the electric field intensity, or in other words, let me repeat it for the last time, electric field intensity, or in other words, the force experienced by +1 Coulomb charge, which is the universal judge charge. Okay, that point is the field point. So now we won't write it +1 Coulomb here, it is now understood. So in order to find that electric field intensity, what we need is the distance between the source point, this is the source point where the source is located, and the field point where we want to find out the field, or where we have placed +1 Coulomb charge, and where now we want to find the force experienced by that judge charge. So that the distance of that field point is from origin is, let's say, this is R, and it is customary to write R prime for every entity which is associated with the source. Okay, so since there is source, we are using the position vector R prime to locate that source point, and to locate the field point we are using the position vector, standard position vector R. So this vector is what we require. Okay, so let's say this is positive charge, and now the judge charge is positive, we don't need to know that. So force experienced by the judge charge now will be electric field intensity, which will be equals to QS divided by 4 pi epsilon naught, this R, magnitude R squared into a unit vector in the direction of this vector R, or I can write it like this: QS 4 pi epsilon naught magnitude of R cubed multiplied by vector R, the same thing. So now it is implicit that, you know, 1 Coulomb is here, and that 1 Coulomb, if you know that 1 Coulomb is implicitly written here, but we have not shown it obviously. So electric field is nothing but the force. It is nothing but the force field. That's why we call it that electric field intensity belongs to the vector effect of the electric field, which belongs to the force field category of effects. Okay, you remember there were two categories: force field category and the flux density category. So electric field intensity belongs to the force field category because it is nothing but force experienced by the judge charge. So we can say that electric field intensity is nothing but force. So every force field is every electric field is force field, but every force field is not electric field. We can say it like this. All right, so now if we know that this vector R is nothing but R prime plus R is this R. Okay, so this plus this is equals to this. So this is equals to this minus this, r minus r prime. So I can replace it over here. Electric field is Qs. So it is nothing but a specialized Coulomb law, you can say, Coulomb's law, in which we have made the second charge to be equal to plus 1 coulombs. Okay, so this cube multiplied by r minus r prime. This is what this should look like. Okay, so if I want to just get rid of this s, if I would represent the source by just q, so I would have to get rid of this as well. So this is the formula for finding electric field intensity, and we always measure electric field intensity in volts per meter. Okay, so I hope it's clear. It should be clear to you now. So since this is nothing but Coulomb's law, as I just said, superposition can be applied to it. So what I can do here, instead of finding the field at this point due to this charge Q1, and now I have got two charges. Okay, let's say another charge Q2 is here, and I want to find, and that charge can be positive or negative, and I want to find, just to illustrate, I am taking it to be positive. All right, so the field at this point, remember that, will act along this line, and that will be pushing the judge charge away. So the force will be in this direction, or the field will be in this direction, because now the field is experienced by the judge charge. So earlier I needed this vector r1, now I would need vector r2. Okay, so to get this vector r2, now from the position vector of this q2 from origin obviously is, let's say, r2, but now we have to add prime because this is also source. This was source, so now the position vector which is locating q1 is r1 prime, position vector which is locating q2 is r2 prime, and the position vector which is locating field point is r, so field point is only 1, so we don't need to add any subscripts. So since it's linear, we can apply superposition. So I can write that field at this point due to charge q1 is q1 upon 4 pi epsilon naught r1, which is nothing but r minus r1 prime. So r minus r1 prime cubed multiplied by r minus r1 prime. And similarly for the second case, the field at this point due to charge q2 will be q2 r minus r2 prime divided by 4 pi epsilon naught magnitude of r minus r2 prime cubed. So the total electric field will be the sum of the individual fields. So generally we can say that there can be n number of point charges. So we can say that generally, due to n number of point charges, the field at any point is nothing but qm divided by 4 pi epsilon naught r minus r prime m divided by its magnitude cubed, where m is summation from 1 to n, where n is the total number of point charges due to which we need to calculate the field. So this is always measured in volts per meter. All right. So you can see that we don't need any subscripts, unnecessary subscript to make our expression look really difficult and complicated, because everything is now here in this case, in the case of n number of point charges as the source charges, and or only one charge as the source charge. We don't need any subscripts, additional subscript to clarify anything. The expression of the electric field intensity in both the cases, for the case of 1 point charge and for the case of n point charges, the expression is nice and clean and clear. We don't need any subscript to add and make it look complicated. So things are, I hope, quite clear. So let's see what happens if we have cluster of charges. Instead of n point charges spaced quite large, with spaces quite large among each other, what if we have cluster of charges so closely packed that we cannot find the distance between the point charges? So in that case, what would we do? Let's see that. So before moving on to the cluster of charges which are very closely spaced, I have got an example, a very simple case in which we have got only 1 point charge of the value q, and we want to find the electric field intensity surrounding this point charge. So this example should show you that how clever and intelligent choice of a coordinate system can simplify things. Let's say this is the case that we are given only 1 point charge q, and we are asked to find an expression which will give us the formula for, or expression for, electric field intensity of this kind of source, which is one zero-dimensional point charge. If now we have got a choice either to use a cylindrical coordinate system, rectangular Cartesian coordinate system, or spherical coordinate system, and let's say we have made an intelligent choice that by using some intuition and intelligence, that this is, if it is the source, then and that source is zero dimensional, so the field surrounding this can be spherical in nature. So let's try to put it at the center of at the origin of a spherical coordinate system. Let's use a spherical coordinate system and make this source charge the origin or the reference, and now try to give the expression for electric field intensity in this case. So we know that at any point, let's say this is the field point, or at this is the field point, whatever the field point may be, the distance between the source and the field point is what we need in order to find the electric field intensity. All right, so the field point, let's say P, is given by r, theta and phi in a spherical coordinate system, where r is nothing but, if you join this point by the origin, what you'll get? You will get the radius r, and the radius r, okay, and this radius r is not only the length, but is also this the radius of the sphere on which this point lies. You should now know that. And the angle it makes with respect to z-axis is theta, and if I drop a perpendicular from here to here, okay, where this perpendicular intersects xy plane, then this is phi. We all know that. So this is r. Okay. Now I want to write the expression for electric field intensity. The charge is q. Okay. At the denominator we need 4 pi epsilon naught. Okay. And what is this? R minus r prime is the distance between the source and the field point. The distance between the source and field point is what? Is small r now. Okay. So what we have is small r. Remember that this small r is not, right now it is not representing any position vector. That's why I haven't drawn any bar over it. This r is the radius or length of this line, okay, which is this coordinate. This r is no more position vector. This is one of the coordinates, okay, one of the coordinates of spherical coordinate system. So this is a quantity, length. It has nothing to do with any vector. So this length, you just cube it, take square of it, and multiply. And this direction is what? We all know that if we are at this point, okay, we are on a spherical surface, and this is positive charge. This is also, since we are interested in electric field intensity, +1 Coulomb jet charge is here. Let's say this is positive charge. So the force will act along the line joining the field point and the source point, all right? So the force will be repulsive because this charge is positive. So if from here I am moving in this direction, or the direction which is joining the field point and origin, this line was r. So what is this direction? This direction can be represented in terms of primitive unit vector small a r. So this direction is a small a r. So wow, you can see that this expression has been reduced to this expression if we had made an intelligent choice of coordinate system, and intelligent choice of keeping it at some origin, keeping the source at the origin. Had we used some other coordinate system, let's say if we had used Cartesian coordinate system, then the situation would have been totally different. In that case, point P would be represented by x, y, and z, all right, and we would not have any primitive unit vector to point in this direction. This time we had the in the case of a spherical coordinate system, we had primitive unit vector ar to point in that direction in which the force lies. So if we had used Cartesian coordinate system, in that case this formula would be written like this: q upon 4 pi epsilon naught r minus r cube. Now this r minus r cube, r minus r prime is nothing but this length. So now since we are in Cartesian coordinate system, we'll have to find position vector that starts from 0 and ends at point P, and that would be, you know, x square plus y square plus not x square y square, rather that would be x ax plus y ay plus z az. Okay, unit vector, because we have got the coordinates of the head x y z, coordinates of the tail 0 0 0, x ax, y x minus 0 ax plus y minus 0 ay plus z minus 0 az, divided by its magnitude cubed. So its magnitude is given by under root x square plus y square plus z square cubed. So you can see that this simple and nice formula, and this we have got a very complicated formula as compared to this one. So a smart choice of coordinate system definitely helps us in writing the final expressions. Yeah, that's it for today, and from next class inshallah we'll move on to discuss the electric field intensity of a cluster of charges which are so closely packed that we cannot measure the distance between 2-point charges, or if we have a continuous charge distribution which is occupying some volume, or if we have a continuous charge distribution which are arranged in one line. So how to find the electric field in those two-dimensional, three-dimensional and one-dimensional charge distributions we'll see in the next class inshallah. So till then, stay safe and fi amanillah. Assalamu alaikum.